So yeah, sorry people on the video, but basically we've just been talking about rehashing. So are there any questions about why we want to rehash or kind of the algorithm for doing it, or are you ready to start coding? Yeah. Yeah, so the load factor is just a number that represents the average length of the linked lists in your hash map. So it's the number of elements in your hash table divided by the number of buckets, right? So it'd be the average number of elements per bucket, and we want that average number to be small so that you don't have to iterate through like a really large linked list, because we're trying to get O of 1, constant runtime. So we want these, we kind of want these linked lists to, on average, be very, very small, like only a couple of elements. Cool. Yeah. So the question is it total number of elements or number of elements in each index? Generally, we use total number of elements, just because so we assume, we'll talk about this in a little bit, but we assume that our hash function does a good job distributing the elements across all of the buckets. So we would assume that our hash function wouldn't just put everything into bucket 0. So it's a pretty safe assumption that you'll have kind of the same number across all of the buckets. And it might be a little bit off, but it won't be too off. Great questions. Okay, so let's talk about how we would implement rehash. So, okay, I included some starter code that's just iterating through our hash map, right? So, generally, when we want to grow the array, we double it just because that's kind of an easy number to get. So, okay, you can say like int hash node star old table equals hash table. We kind of want to copy all of this stuff over so that we have it for the future, right? So if we double our capacity, then we want to create a new hash table, right? So how do we do that? Yeah, does anybody remember kind of how, like, what our hash table type is? It's an array of what? Yeah, hash pointers to hash nodes. Okay, so then we would put in capacity because we want that many buckets. And you put the parentheses so that everything ends up being null. Okay. So, okay. Now down here, table. Right. So down here, okay, we have our current element. We want to put it into our new hash table. How do we know which bucket to put it into? Yeah. Okay. Yeah, so we have like we have to get the hash value and then modify our capacity. So we can call hash code. So you'd say like, okay, so hash equals hash code of cur data. Okay. So we want to put it at the front of our hash table, right? Just like when we did add. People kind of remembering from Friday. Is this making more coming back? So you'd say hash. So you'd say cur next equals full hash table of hash, right? And then we'd say hash table hash equals cur, right? So inserting it into the front of our bucket. Okay. So now we want to get to the next element in our old hash table. So usually we would do like cur equals cur next, right? But what's the problem with doing that here? Yeah. Sorry, I didn't. So it could be that there isn't a next one, but we can catch that up here, right? What is the value of cur next at this point? If we did this, yeah. Yeah, so we basically have lost like the rest of our original list. So we have to make sure that we save that. Next equals cur next. And then down here we can just say cur equals next. Right? Anything else that we have to do in this function? Is there enough memory? Or are we doing everything that we need to do with our memory? Are all our variables correct? Yeah. Yeah, exactly. So basically every time you call new, you want there to be a corresponding delete. So we would say delete of old table. Great. Okay. So we can try running this. Okay. Okay, so we can add. Our add is still working. Okay, our load factor is getting pretty high, right? Our linked lists are pretty long. So we aren't actually calling rehash anywhere. Where do you think we should be calling it? Yeah. Yeah, so you always want to check at the end of your add method to make sure that you haven't, that you don't need to rehash. So we have a helpful function for the load factor. So we can say if this is greater than the max load factor, then we want to rehash. Okay? Okay. Let's see, okay. And now we jump to twice the size. And we had to move all of the elements over. Keep doing that. See, and we jump again. What questions do you have about rehashing? Yeah. Okay. Yeah. So the question is, why do we want to rehash so frequently? So first off, I started off with a really small number of buckets. So this was a little bit disingenuous. I was doing that just so we could see the rehash happen multiple times. But I think also your question is, why do we choose such a low number of elements? And that's because you want even, kind of the biggest buckets to still have a very small number of elements. So you can kind of think if you were just to not use a hash function and randomly assign numbers, like bucket numbers, to all of your elements, you would have some buckets are going to be longer than others. So you want even like the longer buckets to kind of have this upper bound of only having a couple elements. So that's why we choose such a small load factor. Another answer is that it's more important that contains is fast than that add is fast, right? And this is still it's kind of like vector where doubling the size of the array isn't that costly, right? Because you aren't doing it that frequently. So sort of a multitude of reasons. Cool, yeah.
So like when we did priority queue, we could just call delete and then brackets on a whole array structure, but when we had a linked list, we couldn't do that. We had to like go through and like recursively or like use the while loop to destroy the links. So when we're clearing up the memory in the rehash function, how does it know to delete all of the linked lists in this like array of links?
So the question is when you for a priority queue, we called delete with the brackets on the array, and that was totally fine. But when we had the linked list priority queue, you had to actually delete all of the nodes. Hopefully this isn't a surprise to anybody. And then, so why is this that we're just deleting the array down here instead of also going through and deleting all the linked nodes? So yes, if you were actually trying to delete the entire structure, you would have to delete the nodes. But these nodes still exist in our new hash table. So we don't want to delete the nodes because we still want the same elements in our bigger hash table. So that's why we aren't doing that. The better question is, why aren't we doing it up here? And I think that's because Marty just hasn't, this is the starter code from Friday's lecture, and I think Marty just he made a note that you should do this. So it's pretty easy to extend to do that, and definitely a good thing to do if you were implementing this in real life. Yeah, way up in the back.
What is the distinction between the number of elements in a hash map and the length of the hash map?
Great. So the question is, why is there this distinction between the number of elements in your hash map and then the number of buckets in the hash map? So you need to know the number of buckets because that's used in the hash code function, right? It returns the hash modded by the number of buckets. And then you need to know the number of elements if you want to do size or like if you want to do a rehash sort of thing. So the number of buckets is really important because it tells you kind of where to look in the array, and the number of elements is more of a property of that particular set. Does that make sense?
So kind of like buckets are like indices.
Yeah, buckets are indices, exactly. Yeah.
And that's the length of the table?
Yes, exactly. So it's also sort of like how you had a size and capacity for the vector PQ, or the array PQ. Yeah. The code or the slides? Okay. Here. Mm-hmm. Right, so you're right that everything in the hash table is a null pointer, but we're getting cur from the old table, and we're kind of iterating through our old table. So old table should not hopefully have everything all be null. Cool. Okay, so in the interest of time, if there are more questions, why don't you come up and talk to me after class, but just to make sure we get through all the material. But these are really, really good questions. Okay. So you might be wondering, this is a hash set. What do we do about hash maps? It's very similar to the BST lecture where we talked about how you could use a BST for a set and a BST for a map, in that you would just, you want to have change your hash node to have like a key and a value field instead of just that data field, right? Because you need to store both pieces of information. And then the idea is some of the function names are a little bit different. Like you would have to implement a contains function, or so you still have contains, but now it's contains key. Instead of having add, you would have put, get, which would return the value. So you'd have to search your hash map for the key and then get the value from that node. But generally pretty similar. One of the big differences is that when you put something in, you have to check to see if it's already in your hash map. And it's not like before where when we added something to our set, we just ignored a duplicate add. Here we would have to actually change the value if there was already that key. So for example, if we were to put this value and change it out to be Chris, then we would want to get rid of Marty here and replace him with Chris, like that. Yeah, is that a question? Okay. Cool. So this then leads to the obvious question of, this was a table of IDs to names, which isn't super useful. It could be useful, but what if you wanted to have names to IDs or something like that? So let's talk about maybe how we could hash a string. So with an integer, it was pretty easy because you could just do something like take the absolute value and mod it by the length of your hash table. But with a string, there's not really like a number equivalent to a string. And hashing really requires this number so that you know which index to look at. Right? So now you might be saying, like, well, does it matter? Could I just like arbitrarily choose a number? How do I find a number? Can I just say they're all 42? So let's talk about what makes a good hash function, and then we can try to think of some good hash functions for strings. So the most important property of a hash code is that it has to be consistent. So if you have two things that are the same, they need to have the same hash value, right? So why do you think that is? Yeah.
So if you put it in Stanford bands,
Yeah, exactly. So basically, if you were to have if you were to hash the element the first time when you're adding it, and you put it in that index, and then when you're searching for it later on, and your hash function returns a different index, then you aren't going to be able to find your element in your hash table. So you're just going to say it's not there, even if it is, right? So basically, our hash set would be useless at that point. Okay. Another kind of caveat to this is it doesn't necessarily need to be the exact same object. They just need to, if it like is equal under some notion of equality, right? So these are two different vectors, but by the end of these 3 lines of code, they have the same elements in them. So even though they're two separate vectors, since they would be considered equal, like if you were to call v1 equals v2, it would return true, the hash codes for those have to be the same, right? Kind of for the same reason. We want, anytime we're looking for a vector with the elements 1 and 3, to be directed to the same index. Okay. So why is it that, so we said that if A equals B, that they have to have the same hash code. But why is it that if A doesn't equal B, that they could still have the same hash code? Yeah. Yeah, so basically, you're exactly right. So basically, there are infinitely many strings, right? There are only like 4 billion integers. So you're going to have 2 strings that have the same number, because you can't like uniquely assign infinitely many strings to 4 billion numbers, right? So that's why we had collisions before. And it's okay for a hash function to have collisions, because really it's unavoidable. Okay? So what we just talked about is something a hash code has to have, because if it doesn't have that consistency, it's not going to work. Your hash set won't be able to find the elements that you put in. A desired quality, it's not strictly necessary, but a desired quality is that the hash values be well distributed. So that, when you are mapping, or when you are coming up with a hash function for all the strings, you kind of try to use all of these 4 billion numbers, not just 10 of them, for example. So why do we want this property? Why is this important? Yeah. Yeah, exactly. So if you have a better distributed hash function, you're going to have better spread between all of the buckets. So the actual length of your linked list is going to be very close to the load factor. And we said our load factor is small, so it works out really well. However, if you were to have a poorly distributed hash function, like, in an extreme example, you could just end up with, you have a linked list, like a single linked list with all your elements. So it doesn't matter how big your array is, you would still have everything in the same bucket, and that's not going to be an O of 1 runtime, right? Cool. So keeping that in mind, so a valid hash function has to have that consistency, and a good hash function has to be well distributed and also consistent, because you can't have like a good but invalid hash function, right? What do you all think of this hash function? How many people think that it's valid? Okay, how many people think it's not valid? Okay, how many people think, so it is valid because when you put in the same string, you're going to get out the same number, because every string gives you the number 42. Right, so it is valid because you will be looking in the correct bucket. However, is this a good hash function? How many people think yes? How many people think no? Yeah, this will be the linked list example. So this is a really hard way to implement a linked list, right? Yeah, so this one would be valid but not good. Okay, what about this one? So where we just randomly assign an integer. How many people think that this is valid? How many people think it's not valid? Yeah, exactly. So this one's not valid because you would get 2 different random integers when you put in the same string. Okay. What about this one where we put in the memory, we return the memory address of the string, which is a number, right? So how many people think this is valid? How many people think this is invalid? Yeah, so this one's a little bit harder because you could have two strings in your main function that are the same, like they both are hi dude, but they're at different memory addresses because they're different variables. So yeah, that in this case, this would be an invalid hash function. Okay, what about this one? How many people think this is a valid hash function? Just use the length of the string. Okay, yeah, you're exactly right, because if your string length doesn't change, you're going to get the same bucket. How many people think this is a good hash function? Yeah, this is like kind of meh, right? It's better than always returning 42, but if we were trying to hash all of the words in the dictionary, there aren't that many different lengths of words in the dictionary, right? So even if we were to have an array of size 100, you aren't really going to get elements in the 99th and 100th buckets because the English language doesn't have words of that length. So better than 42, I would say still not great. What about this one? So this one is, let's just return the value of the first character of our string. So how many people think this is valid? Yep, two strings are the same. They have to have the same first characters. What about this one? Do you think this one is a good hash function? Do you think it's better than the previous one? How many people think it's better than the previous one? How many people think it's worse? How many people think that this is still like kind of meh, we can definitely do better? Yeah, good intuition. So this one I would say is better just because, if you're hashing all of the words in the dictionary, that gives you 26 options, which, yes, there aren't a lot of words that start with X, but there are probably more words that start with X than have length 26, for example, right? Cool. Okay, so let's try to do a little bit better. Why don't we just add up all of the words, or all of the characters in the string and return that number, right? So this is sort of a hybrid of the last two. So is this valid? Yeah. Okay, is this good? Better than the last one? Okay. So what sort of things are going to have collisions in this hash function? Yeah.
So if words are anagrams of each other, their hashes are going to be the same.
Exactly. So words that are anagrams are going to end up hashing to the same bucket. So probably still not great. Definitely improvement over the last two because you're getting a wider range of values and you're probably getting a little bit of a better distribution. So this is another lecture. Chris Peach did a simulation with a bunch of article titles from Wikipedia, and he hashed all of them using that hash function we just saw. And so it's a little bit, it might be a little bit confusing, but essentially red means that these buckets are really, really long. White means that the buckets are empty. And we represent this as a window instead of as a line because there are so many hash buckets, right? 50,000. So basically, anytime you see white, it's an empty bucket. Anytime you see red, it's a really, really full bucket. So this isn't super well distributed, right? There's a lot of white. So, okay. What if we try to solve that anagrams problem and also try to get a better distribution to fill in some of this white by having this weighted sum? So the idea is, okay, let's have each position of the string, that character value multiplied by a power of a prime number, just to kind of get better distribution. So the idea would be, the 0th index is just itself, and then the first index is the character multiplied by 31, and the second index is like itself multiplied by 31 squared, and so on, just to get a better distribution. Does that make sense? Kind of what we're doing here? Okay. So, and we also want to be prime. Just in general, hashing works better with prime numbers. So if we were to this is actually what's used in Java, is this hash function for strings. So it starts off with just this like random kind of big number just to also increase the spread so it doesn't all start off at 0. And kind of returns like that power structure that we had. So you can still have some collisions, like these two would happen to collide, but it's better than before where all the anagrams collided, right? Yeah. Yeah, so the question is, okay, this function is going to return a huge number. So where does that modding take place? And basically, a good way to think about hash functions is you want them to work on any number of buckets. So a good hash function should really return the entire range of 4 billion integers. And then it's up to the user of that hash function to modify the number of buckets. Because if we assumed an upper bound of like 17, for example, then when we wanted to rehash to 34, we aren't going to get the benefits of rehashing. So yeah, basically the modding part comes in at the point you're using the hash function, not when you're writing the hash function. Great question. Yeah.
So the way it's written right now, let's say that the hash depends only on the last character. Is there supposed to be a plus equal on that hash?
Yeah. Yeah, this should be, no, because, okay, so hash originally is 5381, and then 31 times 5381 plus, like, yeah, so it wouldn't really have a plus equals because it's sort of included here. But, yeah, cool. Yes? Yeah, so it has to do with how ASCII is, like the ASCII values of these characters. Basically, F is 1 bigger than E, and capital B is 30 away from A. So you end up with, if you were to actually try to decode this into the ASCII values, which I don't know offhand, but something like A is 97, B is 98, and like uppercase numbers or something different, or uppercase letters, sorry. So if you were to actually decode this, it has to do with how far away these letters are from each other. Cool. Do you have a second question? Yeah. Mm-hmm. Yep. So it has to do with, I think these slides are like kind of, I think this is the opposite of this, but the idea is like the 0 character would be multiplied by hash 31 times the length of the string, or like 31 to the power of the length of the string number of times, right? So you're multiplying, that's how many times you end up multiplying hash by, 31. Does that kind of make sense? Yeah. The super nitty gritty details of how this works is not super important. Like you won't be asked to develop a really good string hashing function probably ever in your life. That's not really how, like at this point we've just found good hashing functions and we continue using them. If you want to go really deep into security or cryptography, that sort of thing, maybe you would. But in general, computer scientists don't develop new hash functions. It's just important to understand like why this one distributes the values well. Okay. Yeah.
How come you cast in the length to end? Isn't S not like
S.length is technically, it's like an unsigned integer because it can't ever be negative. And so if you compare an int to an unsigned int, you sometimes get like a compiler warning. So I think that's why. So I think literally this was like copied and pasted from the Java source code. So they don't want to have compiler warnings in the Java source code. But yeah, it isn't int, it's just like a special unsigned int. So it can't have a negative value. So if you compare like -1 to something that can't take a negative value, there's like some weird stuff that goes on. Okay, cool. So this was our original. This is with the new hash function, right? So like blue is really good because that's buckets of size 1 to 2. So you have a very good spread. There's a lot less white, there's a lot less red. So our average bucket size is a lot smaller. Cool. What questions do you have about identifying if a hash function is good or valid, that sort of thing? So that's a great question of like, how do you know if a hash function is well distributed? So actually, one of the things that people do is they, they run simulations to see, on this sort of data that I want to use this hash function for, is there a pretty good balance, right? So the hash function that Facebook uses for creating a, hash map of names or something might be different than the hash function that might be used to like show Wikipedia articles, because those are two different kinds of strings. So there is some guesswork involved. There is running simulations. Generally, like, it's hard to say this is the optimal hash function, but you should be able to kind of get a feel for, if you were to compare these two hash functions, which one is going to get a better distribution. Great questions. Okay. So where this comes into play for you, because I already told you will likely in your life never have to write your own hash function for strings, is you will have to write a hash function for objects that you create. So if you were to just create like something called a point, and you try to put your point into a hash set, the hash set's going to be like, I don't know how to hash your point, so I give up and give you an error, right? Just because there's no hash of point. So in order to fix this, you would have to write your own hash code function and an equals operator. So the equals operator, just if the two objects are considered equal to in your eyes as the designer of that class, then you'd return true. So in this case, 2 points are equal if their x coordinates match and their y coordinates match. Though you can think there might be different requirements. And then you can also look at, with the hash code, you have to think about, how can I really combine these parts of my class? So generally, we have good hash functions for the basic types like ints or strings. And so you would need to come up with some way to like weight those or balance those or add those parts together to make your own hash function. And that's kind of what happens. So in this case, we're just like multiplying by two different numbers to get a better spread. Cool. It's actually kind of similar to our final version of our string hash function, where we were weighting all of those characters differently. Okay. So in summary, we have gone through a lot of different implementations of a set, and we have found one that is O of 1 across the board, which I feel like is a really, really cool part of computer science. Like, the fact that we can do this is amazing. And because of this, there are other really cool things you can do in computer science that like we would not have been able to do if you didn't have these constant time guarantees on this data structure. So yeah, it's actually, there's a joke where if you're in an interview, like a software engineering interview, and somebody asks you, oh, how can you do, solve this problem? If you have no idea, just say hashing and you're probably right. So yeah, because it's that good. So many things in computer science just come down to, if you hash things, then like suddenly your problem is so much easier and you can do it so much more quickly. Okay, so hashing is important in computer science because it's good for tech interviews and it's good for hash sets, but it's also really important for cryptography. And kind of the idea behind this at like a very high level is, if you wanted to store a list of passwords, you could store it like this, right? But then anybody who looks over your shoulder at your computer is going to see all of these passwords, right? And so, yeah, that's really bad, because now all of you know my password and could log in as me, right? And then you reassign grades or whatever. Like, that would not be a good system. So one idea is, why don't we just kind of put this into code? And one way we can put it into code is we can hash it, right? It's because hashing will give us this kind of random looking number. There's not really a lot of intuition between why this number came from password 123. And it's hard for somebody to go back and figure out what that number originally was. There are some caveats with this, which is your hash function, it's not enough just to be valid and well distributed, right? You also want to have, generally they don't just make it 4 billion, They make it like some huge number because you really want to avoid collisions, right? Because you could sit, like, if Eve is great and password 123 hashed to the same value in your hash function, then you're going to end up with, like, Marty could accidentally log in as me, right? So you don't want people to be able to kind of like guess passwords randomly and then get into your account. So we really want to, as close as possible, minimize the number of collisions so that these hash functions or these hash codes really are unique for the password. The other tricky part is that we want this to be what's called a one-way hash function, which basically means that looking at this number, it's not easy to figure out what the value, like the original value was. So our int hash function was you take the number and you mod it by 10, it was the absolute value of the number, right? So I could take, like, if I were to look at the hash function, which is the absolute value of the number, I can pretty easily figure out what your password was, right? Like, there are two options. There's the number and the negative number, right? So we want to create this, what's called a one-way hash. There are examples of this. SHA-256 is what's generally used. Again, you will probably not, like, this is just, if you are doing something that requires passwords, people just use SHA-256. They don't write their own hash function. What questions do you have about how hashing is used in cryptography? Yeah. So the question is, like, if you use SHA-256, couldn't you figure out the password? So there are kind of a couple of different ways that you might attack and try to figure out what the password is. So one example is, okay, I could be just looking at a form. Like, I've typed in your username, and I just start with, like, A, B, C, D, right, and go down. So the problem is there's so many combinations of password, or so many unique passwords, that would take it forever, basically. So what they do instead, like hackers usually do instead, is they would get like a large number of passwords. And so these passwords are all hashed, but if you can, like, you get access to the hash function, you try running like the word password through it. And then if that matches a bunch of different users in that file, then you know, like, okay, their passwords must be password, and so on. So that's called a dictionary attack, and that's kind of the more common way. You can't, if I were to just give you a random SHA-256, there's not a way to, like, reverse engineer what the password originally was besides just trying all the different combinations. Great question. Yeah?
How hard is it for a hacker to get access to the file that has the usernames and passwords?
So the question is, how hard is it for a hacker to get access to, like, this file? It's not that hard. It's something that should not happen, but something that does happen. So, like, I've never done it, so I guess I can't really say how hard it is, but it is something that happens, every couple of months. There are also ways to prevent the, like what I was just talking about, the dictionary attack. If you, like, basically you can give every user, like, a number based on what number they were to sign up for your site, and then you kind of hash a combination of the number with their password so that you wouldn't be able to just try, like, password and get a whole bunch of hits. You'd have to try, like, password, comma 1, password, comma 2, right? So it would still take forever. Yeah, so, like, the LinkedIn password dump didn't do that, and, like, that was why that password dump was really bad. If you heard about that from, like, 2012, I think, 2011. Kind of infamous. Always salt your passwords, kids. Yeah, it's called salting. Yeah. Okay. I also wanted to, we have a little bit of time left over, so I wanted to talk about another way to set up your hash table. So as a fun fact that you can tell all of your friends, like something you learned today in CS 106B, there's a type of bird called a cuckoo bird that lays their eggs in other birds' nests. They kind of kick out, like, the original birds and make these new parents, or, like, these parents of these birds care for their child. So this is relevant because it leads us to something called cuckoo hashing. So the idea behind cuckoo hashing is, what if we made contains really, really fast? Like, we guarantee that we only have to look in 2 places. There's no linked list or anything like that. We just only are going to be looking at 2 values max. So in order to do that, what we can do is we can have 2 different arrays, like 2 different hash tables, and have each one of them have a different hash function. And so we can try putting the element into like both of them, and then we just pick like an empty spot, right? And so so when you're searching contains later on, you would only have to look at each of those 2 spots. The bad thing about this is add becomes a little bit harder, because when you add, you might have to kick out an element that was already there and move it to the other hash table. So that's why it's called cuckoo hashing, because it's kind of like what the birds do. So as an example, if we wanted to, so it's important that they have 2 different hash functions, because if they were the same, then like something that collides will collide in both hash tables instead of just in one, right? So if these are 2 hash functions, when we insert 3, we can just like randomly choose this to put in this array over this array. And this is 9 mod 4, which is 1. So we put 6, so that's 13 mod 4, which is also 1. Okay, 5, so 15 mod 4 is 3. Or 10 plus 1 is 11, mod 4 is 3. We insert 7. So when we insert 7, you get 21 mod 4 is 1, which we put in this spot, and 15 mod 4 would put in this spot, right? So our issue with that is, okay, we'd have to kick one of these 2 out. So let's put 7 in, we choose this one randomly, and then we would move 5 over to the other table. And so then this would be putting in this spot, right? So add becomes a little bit longer, because you could imagine like maybe there was something already in this spot, and then you have to move that back over to this table, and so on and so forth. But what's really cool is when you search for contains, you only have to look at these 2 spots. You don't have to look anywhere else. So contains is really, really fast, because it maxes out at only looking at 2 elements. Yeah? Yeah, so the question is like, could you end up in this cycle where, you know, like we put 5 over here, and then we kick like 6 over here, and or you know, like 4 over here, and then we have to kick 6 over here, and then 3 here, and then 7. And now 7's going back where the 5 is. So like, could you just end up in this loop? And yes. So that's, with this one, the implementation's a little bit harder, because you do have to track for those sort of loops. If that happens, you create like a new hash function basically for one of your 2 tables. And then also you have to be really careful to make sure that you are rehashing when necessary, because you can imagine if there's only 1 spot left in your table, you're going to have a really, really long add time. So, great question. The point of this is to show you there are lots of ways to set up use hashing. So this is a little bit better when it comes to contains, but a little bit worse when it comes to add. So there are lots of different ways that you can use hashing to make a hash set. We just told you about a really common one, and now cuckoo hashing. Cool. Any last questions about hashing? Anything we learned today? Okay. Have a great rest of your Monday.